And now in this lecture we'll find out the area of the green semicircle. In the drawing we have two semicircles. This is the white semicircle, this is the green semicircle. In addition, you know that this is line segment AC, this is equals to 5 units in its length. This is line segment CB, this is equals to 1 unit in its length. Again, our mission is to find out the area of this green semicircle. So we start with the first method, and we join points P and B together by a straight line. In the next step, I'll copy the white semicircle in a new page and we'll implement rule 7 on the white semicircle. So actually, this is the white semicircle that according to the original drawing. AB is the diameter of this semicircle, so I'll write it down. AB is the diameter of this white semicircle. By joining points P and B together by a straight line, we can deduce peripherical APB. This is peripherical APB, and peripherical APB is subsetted on AB. This is the diameter of this semicircle. So here we can implement rule 7. I'll repeat quickly on rule 7. According to rule 7, if a peripheral angle is subtended on the diameter of the circle, then it is equal to 90 degrees in its size. So in the drawing we have a circle, and we have this is line segment AB, this is the diameter of this circle, and we have here this is peripheral angle ACB, that is subtended on AB, that is the diameter of the circle, and therefore peripheral angle ACB equals to 90 degrees in its size. So whenever you have a peripheral angle that is subtended on the diameter of the circle, it must be equal to 90 degrees in its size. So we can actually implement rule 7 in our drawing. Why? Because in our drawing we have peripheral angle APB that is subtended on AB, that is the diameter of this semicircle, therefore peripheral angle APB according to rule 7 must be equal to 90 degrees in its size. So this peripheral angle APB equals to 90 degrees in its size. According to rule 7. In the next step, we join points P and C together by a straight line. Next step, I'll copy the green semicircle, this green semicircle in new page, and again we'll implement all 7 on this green semicircle. So here, this is the green semicircle that I go to the original drawing. AP is of course the diameter of this green semicircle, so I'll write it down. AP is the diameter of this green semicircle. By joining points P and C together by a straight line, like that here, peripheral angle ACP. This peripheral angle ACP is obtained on AP, that is the diameter of this green semicircle. Therefore, according to rule 7, peripheral angle ACP must be equal to 90 degrees in its size. So this peripheral angle ACP is a right angle. Here we have, this is angle A. This angle A is a common angle that belongs to both triangles. Angle A, this angle A, this angle A belongs to the green triangle APC, and it is also belongs to triangle APB. Therefore, angle A is a common angle that belongs to both triangles. So we'll define the common angle A as alpha. This is the common angle A, this is equals to alpha according to our definition. So in this right triangle APB, this angle equals to alpha, this angle equals to 90 degrees. Therefore, this third missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equals to 180 degrees. That is the sum of the angles in any triangle. Likewise, this is angle A, that is equals to alpha according to our definition. So in the green triangle APC, the green right triangle APC, this angle equals to alpha, this angle equals to 90 degrees. Therefore, this first missing angle must be equal to 90 degrees minus alpha. in the next step, I copy this white triangle APB and this green triangle APC in the new page, and we prove that those two right triangles are similar to each other according to angle similarity rule. So actually, this is the green right triangle APC that I copied from the original drawing, and this is the white triangle APB that I also copied from the original drawing. So in the next step, we prove that those two white triangles are similar to each other. And prove that this white triangle APB similar to this right green triangle APC. So why those two right triangles are similar to each other? First of all, those two angles, they are both equal to 90 degrees, therefore they are equal to each other. So actually this is angle APB. In the right triangle APB, and it is equal to this angle, that is actually angle ACP, the green triangle APC. Repeat again, angle APB, the right triangle, equals to angle ACP, the green triangle. They are both equal to 90 degrees, therefore they are equal to each other. In addition, this is angle alpha, this is also angle alpha. So angle alpha is a common angle that belongs to both angles, so we can find out that angle alpha equals to itself is a common angle that belongs to both angles. So if we relate to angle alpha as it belongs to this right triangle APB, it will be defined as angle PAB. And it equals to itself. So if you relate to angle alpha as it belongs to the green triangle APC, it will be defined as angle PAC. repeat again. This equation means that angle alpha equals to itself is just called to angle alpha two different names. Angle alpha equals to itself is a common angle that belongs to both triangles. And finally, those two angles, they are both equal to 90 degrees minus alpha, therefore they are equal to each other. So actually, this is angle ABP. The right triangle APB, and it is equal to this angle, that is actually angle APC. The green triangle APC. Repeat again. Angle APB in the right triangle equals to angle APC in the green triangle. They are both equal to 90 degrees minus alpha, therefore they are equal to each other. So we actually proved that all the fingers of this right triangle APB are correspondingly equal to all the fingers of this right green triangle APC, and therefore those two right triangles are similar to each other according to angle similarity rule. So I write it down. The right triangle APB is similar, this is the sign of similar, to the right green triangle APC. According to angle similarity rule. And from the fact that those two right triangles are similar to each other, we derive that the following relationship exists between their sides. We derive that side AB in the right triangle over side AP in the green triangle equals to side AP in the white triangle over side AC in the green triangle. This again, we derive that side AB in the white triangle over side AP in the green triangle equals to side AP in the white triangle over side AC in the green triangle. What is the length of AB? From the drawing, it is very easy to see that AB in total equals to 5 plus 1, that is 6. So AB equals to 6. We substitute AB by 6. So it is 6 over AP. AP is the missing side, so we leave it as it is. And it is equals to AP over AC. The length of AC equals to 5 units according to what is given as the question. So in conclusion, we can find out that six over AP equals to AP over 5. Here we cross multiply this equation and we get that 5 times 6 is 30. 30 equals to AP times AP, that is AP squared. So 30 equals to AP squared. We take a look out of this equation. And finally, we find out that the missing side AP equals to the square root of 30 units in its length. So okay, this is the missing side AP. is equal to the square root of 30 units in its length. AP is actually the diameter of this green semicircle. If AP is the diameter, it means that AP over 2 is the radius of this green semicircle. So the radius R of the green semicircle equals to AP, the diameter AP over 2. AP is equal to 30, therefore AP over 2 is equal to 30 over 2. In conclusion, we can find out that the radius of the green semicircle equals to the square root of 30 over 2 units in its length. The radius of this green semicircle equals to the square root of 30 over 2 square units. Again, our mission is to find out the area of this green semicircle. So the area of the green semicircle equals to pi r square over 2. Because again, the area of the green semicircle equals to pi r square over 2. So it is equals to pi r is equal to 30 over 2. Therefore r square is equal to 30 over 2 square divided by 2. So the area of the green semicircle equals to pi, and square root of 30 square is 30, over 2 square is 4 divided by 2. So the area of the green semicircle in total equals to pi, and we have 30 over 4 over 2 is 30 over 4 times 2, and here we have 30 over 2 is 15, so in total the value of this expression equals to 15 pi over 4. 15 over 4 is 3.75, therefore in total this expression equals to 3.75 pi. So we shall find out that the area of the green semicircle equals to either 3.75 pi square units, so in terms of numbers, this equals to 11.78 square units. Because again, we should find out that the area of this green semicircle equals to either 3.75 pi square units, so in terms of numbers, this equals to 11.78 square units. We finished with the first method. In the next step, I will present to you how to find out the area of this green semicircle according to the second method. In the second method, we join points P and B together by a straight line. In the next step, I will copy the white semicircle in a new page, and we will implement on this white semicircle rule 7, exactly as we did in the first method. So actually, this is the white semicircle that I got from the original drawing. We know that AB is the diameter of this white semicircle, so I write it down. Now we will implement rule 7 on this white semicircle. Actually, by joining points B and P together by a straight line, we created a peripheral angle APB. This is peripheral angle APB. In this peripheral angle APB subtended on AB, that is the diameter of this white semicircle, and therefore according to rule 7, peripheral angle APB must be equal to 90 degrees in its size. Okay, so this peripheral angle APB equals to 90 degrees in its size. That is to say, line segment BP is perpendicular to PA. Again, line segment BP is perpendicular to PA. But PA is the diameter of this green semicircle. And you know that the center of any circle must be located on the diameter. So this is the center of the green semicircle. We define the center as point O. Point O is the center of the green semicircle. Point P is a point on the green semicircle itself. So this is exactly the definition of a radius. Therefore, OP is the radius of this green semicircle. We define the radius of this green semicircle as R. Therefore, OP equals to R. Again, we know that BP is perpendicular to PA, so this angle equals to 90 degrees in its size. If BP is perpendicular to PA, BP must be also perpendicular to the radius PO. Again, if BP is perpendicular to PA, BP also must be perpendicular to the radius PO. In conclusion, we can write down that line segment BP is perpendicular to the radius PO of this green semicircle. Okay. BP is perpendicular to the radius PO of the green semicircle. Okay. Again, BP is perpendicular to the radius PO of the green semicircle. And therefore, we can implement here rule 1. I'll repeat quickly rule 1. A tangent to the circle is perpendicular to the radius drawn to its point of tendency. In the drawing we have a circle. This is line segment OM is the radius of this circle, that is equals to R. And the radius R, that is OM, is drawn to point M, that is the point of tendency of line segment AB with this circle. Whenever you have a radius that is drawn to the point of tendency, then line segment AB will be perpendicular to the radius MO. But what is line segment AB? Line segment AB is a tangent. So we can conclude from it that whenever we have a line segment that is perpendicular to the radius, it must be a tangent of the circle. Why? Because we have line segment AB that is perpendicular to the radius AMO, and line segment AB is defined as a tangent to this circle. So we can actually implement rule 1 in our drawing. Why? Because in our drawing we have this is line segment BP that is perpendicular to the radius PO of this green semicircle, and therefore, according to rule 1, line segment BP must be defined as a tangent to this green semicircle. So I write it down. We actually found out that this is line segment PB. It is actually tangent to this green semicircle at point P. So line segment PB is defined as a tangent to this green semicircle. So actually, if we focus on this common axis point B, from this common axis point B, we have tangent BP to this green semicircle that is tangent to this green semicircle at point P. In addition, from the same common axis point B, we have here chord AC. This is chord AC. That is the chord of this green semicircle. So now we can implement rule 10 in our drawing. I'll click on rule 10. According to rule 10 is true in any circle. In any circle, if AB is a chord of the circle, we have here AB, it is a chord of this circle. And from the common axis point B, we have also tangent PT. This is tangent PT, this is tangent to this circle at point T. So, we can implement rule 10 in our drawing. Actually, before that, in this drawing, the following equation is true. That PT square equals to PA times PB. Again, PT square equals to PA times PB. We can actually implement rule 10 in our drawing. Why? Because in our drawing, from the common axis point B, we have tangent BP that is tangent to this green semicircle at this point P. In addition, from the same common axis point B, we have here tangent, we have chord CA. Chord CA is chord of this green semicircle. So actually all the requirements of rule 10 are satisfied, and therefore we can implement here rule 10. According to rule 10, BP square equals to BC times BA. Again, B square equals to BC times BA. So I write it now. BP square equals to BC times BA. Repeat again. According to rule 10, if we focus on our original drawing, the following equation is true, that BP square equals to BC times BA. BP is the missing tangent, so we leave it as it is, so BP square equals to BC. BC is 1, so we substitute BC by 1, times BA. BA in total equals to 5 plus 1, that is 6. So BA equals to 6, we substitute BA by 6. In conclusion, I shall find out that according to rule 10, BP square equals to 1 times 6, that is 6. So So BP square equals to 6. Here we take out all of this equation and finally get that BP, the misintended BP, equals to the square root of 6 units in its length. So this intended BP equals to the square root of 6 units in its length. In the next step, I'll copy the right triangle APB in a new page and we'll implement the Pythagoras theorem on this right triangle, triangle APB. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the sides of the perpendiculars. So actually, this is the right triangle APB that the correction of the original drawing. According to the Pythagoras theorem, in this right triangle APB, AB squared, that is the square of the hypotenuse, equals to AP squared plus PB squared. And AB squared equals to AP squared plus PB squared. The hypotenuse AB equals to 6 units in its length, therefore AB squared is 6 squared, that is 36. And it is equals to AP squared. AP is the missing side, so we leave it as it is. AP squared plus PB squared. PB equals to the square root of 6 units in its length, and therefore PB squared is square root of 6 squared, that is 6. So in conclusion, we should found out that 36 equals to AP squared plus 6. Here we subtract 6 from this equation. Finally get that AP squared, the missing side, equals to 36 minus 6 is 30. So AP squared equals to 30. We take out all this equation. And finally get that AP equals to the square root of 30 units in its length. AP is the diameter of the green semicircle, and it is equals to the square root of 30 units in its length. If the diameter AP equals to square root of 30, it means that the radius must be equal to half of it. So we define the radius of this green semicircle as R. So the radius R of the green semicircle equals to the diameter AP over 2. The diameter AP is square root of 30. Therefore, the radius R must be equal to the square root of 30 over 2. So if I want to create that the radius R of the green semicircle equals to the square root of 30 over 2 units in its length. Again, our mission is to find out the area of this green semicircle. The area of the green semicircle equals to pi r square over 2. Pi r square over 2. So the area of the green semicircle equals to pi times r square. R is equal to 30 over 2. Here, r is equal to 30 over 2. Therefore, r square is equal to 30 over 2 square divided by 2. So the area of the green semicircle equals to pi, and square to 30 square is 30, over 2 square is 4, divided by 2. So the area of the green semicircle equals to pi times 30 over 4 over 2. 30 over 4 over 2 is 30 over 4 times 2. And here we have 30 over 2 is 15, so in total this expression equals to 15 pi over 4. 15 over 4 is 3.75. Therefore, in total, this expression equals to 3.75 pi. 3.75 pi is 11.78 square units. So, in conclusion, we have found out that the area of the green semicircle, according to the second method, also equals to either 3.75 pi square units, or in terms of numbers, it is equals to 11.78 square units. I'll repeat again. The area of this green semicircle equals to either 3.75 pi square units, or in terms of numbers, it is equals to 11.78 square units. In the next step, I will summarize the lecture. In this lecture, we found out the area of this green semicircle using two different methods. We start with the first method. In the domain, we have two semicircles. In addition, we know that this is line segment AC that is equals to 5 units in its length. This is line segment CB that is equals to 1 unit in its length. Again, our mission is to find out the area of this green semicircle. So in the first method, we join points P and B together by straight line, and then complete the white semicircle in a new page, and we implemented 7 in the white semicircle. This is the white semicircle that I call it from the original domain. AB is of course the diameter of this semicircle. Here, by joining points P and B together by straight line, we created peripheral angle APB. Peripheral angle APB is subtended on AB, that is the diameter of this white semicircle, and therefore, according to rule 7, any peripheral angle that is subtended on the diameter of the circle must be equal to 90 degrees in its side. Therefore, peripheral angle APB must be a right angle. As you can see here, this is a right angle. In the next step, we join points P and C together by straight line. And then I copied the green semicircle in a new page, and again we implemented rule 7 in the green semicircle. Okay. This is the green semicircle that I copied from the original drawing. Actually, by joining, first of all, AP is of course the diameter of this green semicircle. And by joining points P and C together by a straight line, we create the peripheral angle ACP. This is peripheral angle ACP. Peripheral angle ACP is subtended on AP, that is the diameter of this green semicircle. Therefore, peripheral angle ACP must be equal to 90 degrees in its size according to rule 7. You see here, this angle is a right angle, and it is a right angle according to rule 7, because it is subtended on AP, that is the diameter of this green semicircle. If we focus on this original drawing, this is angle A. Angle A is the common angle that belongs both to the green right triangle APC, and this angle A also belongs to the right triangle APB. So angle A is the common angle that belongs to both triangles. So actually, we find this common angle A as alpha. So here, according to our definition, this is the common angle A. This equals to alpha. So in this right triangle APB, this angle equals to alpha, this angle equals to 90 degrees. Therefore, this third recent angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in the triangle. Likewise, in the green triangle, APC, this angle equals to alpha, according to our definition. This angle equals to 90 degrees. Therefore, this third recent angle must be equal to 90 degrees minus alpha. In the next step, I copied this green triangle APC in the new page, and also this white triangle APB. And we actually proved that those two right triangles are similar to each other according to angle similarity rule. So actually, those are the two right triangles that I called from the original drawing. So why those two right triangles are similar to each other? First of all, those two angles are both equal to 90 degrees, therefore they are equal to each other. In addition, this is angle alpha, that is a common angle, it belongs to both those two triangles. So we can write down that angle alpha equals to itself is a common angle that belongs to both triangles. And finally, those two angles they are both equal to 90 degrees minus alpha, therefore they are equal to each other. So actually proved that all the triangles in this right green triangle APC correspond equal to all the triangles in this right triangle APB. Therefore, those two right triangles are similar to each other according to angle similarity rule. So I repeat again. The right triangle APB similar to the green triangle APC according to angle similarity rule. And from the fact that the two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive the side AB in this right triangle over side AP in this green triangle equals to side AP in this right triangle over side AC in this green triangle. I repeat again. We will derive that side AB in the white triangle over side AP in the green triangle equals to side AP in the white triangle over side AC in the green triangle. AB in total is 5 plus 1, that is 6, and AC is 5. So here we substitute AB by 6 and AC by 5. And finally found out actually that 6 over AP equals to AP over 5. Here we can multiply this equation. And finally found out that 5 times 6, that is 30, equals to AP squared. So here we took out of this equation and I found out that the missing side AP equals to the square root of 30 units in its length. Okay. This is the diameter of this green semicircle, and it is equals to the square root of 30 units in its length. And the radius equals to the diameter over 2. So the radius R of the green semicircle equals to the diameter AP over 2. The diameter AP is equal to 30, therefore the radius is equal to 30 over 2. In conclusion, we found out that the radius R of this green semicircle equals to the square root of 30 over 2 units in its length. Here R equals to the square root of 30 over 2. Our mission is to find out the area of this green semicircle. The area of this green semicircle equals to pi r squared over 2. I'll repeat again. The area of this green semicircle equals to pi r squared over 2. So it is pi r is equal to 30 over 2, therefore r squared is equal to 30 over 2 squared divided by 2. We open the brackets here and found out actually that in conclusion the area of the green semicircle equals to pi, and square root of 30 squared is 30 over 2 squared is 4 divided by 2. So in total the area of the green semicircle equals to pi times 30 over 4 over 2. 30 over 4 over 2 is 30 over 4 times 2. So in total the value of this expression equals to 30 pi over 4 times 2. 30 over 2 is 15, so in total the value of this expression equals to 15 pi over 4. 15 over 4 is 3.75, therefore the value of this expression in total equals to 3.75 pi. 3.75 pi is 11.78. So in conclusion, we should have found out that according to the first method, the area of this green semicircle equals to either 3.75 pi square units, so in terms of numbers, the area of this green semicircle equals to 11.78 square units. We finish with the first method. In the next step, I actually presented to you how to find out the area of this green semicircle according to the second method. In the second method, we join points P and B together by a straight line. Then I copied the white semicircle in a new page and implemented rule 7 in the white semicircle exactly as we did in the first method. Actually, this is the white semicircle that I copied from the original drawing. Again, by joining points P and B, created there peripheral angle APB. This is peripheral angle APB. And we know that AB is the diameter of this white semicircle. Again, AB is the diameter of the white semicircle. And we have a peripheral angle APB that is subtended on AB, that is the diameter of this white semicircle. And according to rule 7, any peripheral angle that is subtended on the diameter of the circle must be equal to 90 degrees in its size. Therefore, peripheral angle APB must be equal to 90 degrees. Here you can see that this is peripheral angle APB. Is equal to 90 degrees in size according to rule 7. So here we have angle APB is a right angle. What does it mean that angle APB is a right angle? It means that line segment BP is perpendicular to PA. Again, line segment BP is perpendicular to PA. Repeat again. Line segment BP is perpendicular to PA. PA is the diameter of this green semicircle, and therefore the center of this green semicircle must be located between points P and A, because PA is the diameter. So this is the center of the green semicircle that we defined as O. So point O is the center of the green semicircle, point P is the point of the green semicircle itself. So this is exactly the definition of radius. Therefore, OP is the radius of this green semicircle that is equals to R. In conclusion, we shall find out that line segment BP is perpendicular to the radius PO of this green semicircle. Repeat again. We found out that line segment BP is perpendicular to the radius PO of this green semicircle, and therefore we can implement here rule 1. According to rule 1, the tangent to the circle is perpendicular to the radius drawn to its point of tendency. So in the domain we have a circle, and we have this is line segment OM, that is the radius of this circle, and here line segment AB is perpendicular to the radius MO. Again, line segment AB is perpendicular to the radius MO, and therefore, according to this rule 1, line segment AB is defined as a tangent to this circle. Again, line segment AB is defined as a tangent to this circle. It's actually tangent to this circle, it's point M. So whenever you have a line segment that is perpendicular to the radius, the line segment must be defined as a tangent to the circle. Okay? We can implement all 1 in our drawing. Why? Because in our drawing we have this is line segment BP that is perpendicular to the radius R of this green semicircle, and therefore according to rule 1, line segment BP must be defined as a tangent to this green semicircle, and indeed line segment BP is tangent to this green semicircle at this point P. Again, according to rule 1, line segment BP is a tangent to this green semicircle at point P. So from the common standpoint point B, we have tangent BP to this green semicircle at point P. In addition, from the same common standpoint point B, we have this chord CA of this green semicircle. Now we can implement on our drawing rule 10. I repeat quickly on rule 10. According to rule 10 is true in any circle. So in any circle, if AB is any chord, you can see that AB is a chord of this circle, and PT is tangent to this circle point T, then in this drawing the following equation is true, that PT square equals to PA times PB. Again, PT square equals to PA times PB. We can definitely implement rule 10 in our drawing. Why? Because in our drawing, if you focus on this common standpoint point B, from this common standpoint point B, first of all we have tangent BP, that is tangent to this green semicircle at this point P. In addition, from the same common standpoint point B, we extend from the common standpoint point B, we get here chord CA. So all the requirements of rule 10 are satisfied, and therefore we can implement rule 10. According to rule 10, PB square equals to BC times BA. Again, PB square equals to BC times BA. Repeat again. According to rule 10, BP square equals to BC times BA. BP is the missing tangent, so we leave it as it is. This equals to BC. BC is 1, and BA in total equals to 5 plus 1, that is 6. Okay, so we substitute BA by 6 and BC by 1, so in total BP square equals to 1 times 6, that is 6. So BP square equals to 6. We took out of this equation and finally found out that the missing tangent BP equals to the square root of 6 units in its length. This is the missing tangent BP that is equals to the square root of 6 units in its length. In the next step, I copied this right triangle APB in a new page and implemented the Pythagoras theorem on this right triangle APB. We just right now found out that side PB equals to the square root of 6 units in its length, and the opposite AB of this right triangle APB equals to 6 units in its length. This is right triangle APB that I copied from the original drawing. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the sides of the perpendicular. The hypotenuse in this right triangle APB is AB, therefore the square of the hypotenuse is AB square, And AB square must be equal to AP square plus BB square. Again, AB square equals to AP square plus BB square. AB is 6, therefore AB square is 6 squared, this is 36. And it is equal to AP square. AP is the missing side, so we leave it as it is, plus BB square. BB is square root of 6, therefore BB square is square root of 6 squared, that is 6. So in conclusion, we actually found out that 36 equals to AP square plus 6. If we subtract 6 from this equation, we finally found out that AP square equals to 36 minus 6, that is 30. AP square equals to 30, we took out of this equation. And finally we found out that AP equals to, the missing side AP equals to the square root of 30 units in itself. This is the missing side AP, is equals to the square root of 30 units in itself. AP is the diameter of this green semicircle, and it is equals to the square root of 30 units in itself. If the diameter AP equals to the square root of 30 units in itself, it means that the radius must be equal to half of it. Again, the radius of this green semicircle R equals to the diameter AP over 2. The diameter AP is square root of 30, so square root of 30 over 2 is the radius of this green semicircle. And the area of this green semicircle equals to pi r square over 2. Okay, the area of this green semicircle equals to pi r square over 2. The area of the green semicircle equals to pi r square over 2. So, it is pi r is square root of 30 over 2, therefore r square is square root of 30 over 2 square divided by 2. Open the brackets here and found out, okay, the area of this the area of the green semicircle equals to pi square root of 30 square is 30 over 2 square is 4 divided by 2. So in total, the area of this of the green semicircle equals to pi times 30 over 4 over 2. 30 over 4 over 2 is 30 over 4 times 2. So in total, this expression equals to 30 pi over 4 times 2. Here we have 30 over 2 is 15, so in total the value of this expression is 15 pi over 4. 15 over 4 is 3.75, so in total the value of this expression equals to 3.75 pi, and 3.75 pi is 11.78. So in conclusion, in both methods we found out that the area of this green semicircle equals to either 3.75 pi square units, or in terms of numbers, it is equals to 11.78 square units. Okay, thank you very much.